So I'll get started again. Just to remind you where we were, we'd start talking about polynomials and how to multiply them, right? And so we're starting our discussion of factoring, right? So factoring polynomials. And so basically you could think about this as sort of unmultiplying, if you want. So like mathematically, the problem of factoring an arbitrary polynomial, it's a very difficult problem. But in here, we'll try to focus on examples which for the most part we can just do with whole numbers. And then we'll eventually ease into doing some with fractions and so forth, all right? So show you a series of examples here. Suppose we had 3x cubed plus 6x squared plus 9. All right. So the first kind of factoring we should think about is, can we factor a number out of a polynomial, right? So if we've got a common, number, this is what? This is really 3 times x cubed plus 3 times 2 x squared plus 3 times 3 if you look at it, right? So there's this common 3, 3, 3 everywhere. So by algebra, we can factor that 3 out. It's called the distributive property. 3 times x cubed plus 2x squared plus 3. All right? And that would be as far as I would go here. All right? So, I mean, that's an example of factoring anyway. I mean, I could tell you that this polynomial is not factored completely. All right? What I'm trying to say is there is a way to factor this further. All right? But also, I think that it would be pretty difficult for this example to actually do that. So I'm just going to leave it right. I'm going to stop right there. So I'll call that example 1. Example 2. Let's see here. How about if we have 2x squared plus 4x plus 1. And so I'm going to be, I want to actually factor out a 2. Suppose you want to factor out a 2. Can you do that? What do you think? Don't think so? Yeah, I think we can factor 2 out of the first 2 pretty easy, right? But that last one is kind of trouble, isn't it? So let me write something out. So this is 2 times x squared plus 2x and plus something. If I want to factor that 2 out, we're going to have to bring into play our old nemesis, fractions. We need fractions to do that. What would you put? What would you fill in the blank there? A half, right. So if we put a half there, then that's logical, because if we multiply it back out, we'll get back where we started, right? The ultimate test of any factoring is when you multiply back out, do you get back to where you started, right? And if we multiply this back out, we get 2x squared plus 2 times 2, which is 4x, plus 2 times a half. 2 times a half is 1, right? All right. Example 3. What if we had something like x to the 4th plus 3x cubed minus x squared? So let me point out that we can extract an x squared from each one of these terms, right? Like x to the fourth is what? We can think of x to the fourth as x squared times x squared, right? We can think of x cubed as what? 3x squared times x, right? And, well, x minus x squared, right? So, well, x squared, okay, fine. And so my point to you is then we can factor out x squared, and it leaves us with x squared plus 3x, and then what? What's the last term that I haven't written down yet? Not 1. Oh, yeah, minus 1, right? Now, is there any kind of like nice way to factor this quadratic x squared plus 3x minus 1? I'm pretty sure no, there's not a nice way to factor this. So I'm just going to stop there for the moment. We'll eventually come back to there and talk about how to factor. It turns out we can factor any quadratic, actually. So, but I'm going to stick to the nice ones to start with here. So there's that. End of story. Example 4. What if we had x squared plus 3x plus 2? Now this time I'm not going to try to pull a number out. I'm going to actually try to factor this into a product of what are called linear polynomials. So what is a linear polynomial? When I say linear polynomial, that means something of the form mx plus b. That's a linear polynomial. A quadratic polynomial, what does that look like? Something of the form ax squared plus bx plus c, right? What's a cubic polynomial? What's that look like? That looks like something like ax cubed plus bx squared plus cx plus d. What does a quartic polynomial look like? You're like, enough already, stop. Quartic polynomial is something that looks like ax to the fourth plus bx cubed plus cx squared plus dx plus e. What's past quartic? This one, I'll do one more. I'll stop here. This is where the next is up. It's called quintic. Quintic polynomial. Ax to the fifth plus bx to the fourth plus cx cubed plus dx squared plus ex plus f. There you go. So those are all the special names you could, I think, ever need for just generic polynomials. The degree of a linear polynomial is 1. The degree of a quadratic polynomial is 2. The degree of a cubic polynomial is 3. The degree of a quartic polynomial is 4. The degree of a quintic polynomial is 5, right? One, 2, 3, 4, 5. All right. There's one other thing I should mention while I'm on this digression of terminology. There is some special condition we need for these to actually be properly named. Is is it really quadratic if that big A is equal to 0? I mean, if you think about it, if the big A was equal to 0, we'd really just have a linear polynomial, right? So it's also our custom to insist that the leading coefficient is non-zero. So, fine print. M not equal to 0. A not equal to 0. And then these are little a not equal to 0, the way I've written them. Okay, anyway. Sorry, got that out of my system. So we can go back to my factoring example. So I want to take this quadratic polynomial, all right? I want to take this quadratic polynomial. I want to factor it as a product of linear polynomials. So I want to have something like this. And I'm going to put an x here. I'm going to put an x here. All right? And then the game we're going to play, to start with, is we're just going to look at the constant coefficient, which is this 2, right? That's the constant coefficient, the constant term, rather. And think about how to get that. How can we get 2? How about 1 times 2, right? Or minus 1 times minus 2 is another way we could do it, right? So what should I put here? I should try plus 1 plus 2, right? Because 2 is equal to 2 times 1, but it's also equal to minus 2 times minus 1, minus 2 times minus 1. But, these are the natural first things to try. It's like 2 and 1, or minus 2 and minus 1. But the minus doesn't really look like it's a good choice here. And how do I check whether or not this is right or wrong? Multiply it out, right? And so we get x squared and plus x plus 2x, but x plus 2x is 3x, and 1 times 2 is 2, so there you go, factoring. Very similar, example 5. What if we had x squared minus 3x plus 2? Then what happens? Oh, I'll do the easy part. X. So this one, if we try minus 1, right? And we do minus 2 over here, it should work, because if we multiply this back out, we get a minus x and a minus 2x, which gives me a net of minus 3x, which is what we have on the left-hand side. Every time I do a factoring, I'm doing a mental check of if I multiply out my alleged factoring, do I get back where I started, right? I'm multiplying the unmultiplication to see if it worked. I don't always write that out, but maybe you should write that out when you're first learning this. I don't know if you guys are first learning this or if you have. How many people have at least tried to learn factoring before and are bored out of your minds with what I'm doing? Okay, good. That is wonderful. I'm happy. Boredom is good. If what I'm doing is completely mysterious, then that would be much more troubling. So I'll move on. Aw, man. Nice. Second here, I got to get the juice. All right, so example 6. What if we have 2x squared I don't know, 4x plus 3 I meant a 7. All right, so something like this, maybe we should put 2x here, right? Put x over here. And what's 3? Three is what, 3 times 1, right? And we want to get 7 somehow. So whatever numbers we put over here, we need to get that, we somehow create that term of 7x in the middle, right? You got it? Oh. Somebody got it? I think we're going to use plus, right? I don't think we're going to, I don't think we're going to need minus here. I mean, let me do what doesn't work. If I put the 3 here, that's not going to do it, because then we'll get like the 3x, and then from the other one we get what? If I put 3 there, it forces me to put the 1 on the other side. So then I would end up with like 3x plus 2x. I get a 5x for my linear term, but we got 7, right? What's that? Yeah, so what I'm trying to say is I shouldn't put the 3 here. You should put it over here, you know? If I put it over here, then I get this times that, which gives me 6x. And if I put the 1 here, I get 1x plus 6, which is 7. So trial and error is definitely part of how I do this in my head, for sure. Like I try something, I think through it, and I go, oh, wait a minute, that doesn't work. Adjust it a little bit, you know? But see, if I had 2x squared plus 5x plus 3, from what we just talked through, you kind of see what we're going to do, right? We just flip the 3 and the 1 for this one, right? See, because now we get 3x plus 2x gives me back that 5x. Is that good? Let's see here, what else could I do? What if I had 2x squared minus x plus 3? Minus 1? Or minus, where should I put my minus? The first one? And then plus 3 over here? See, but then that's going to give me 6x minus x, which is 5x. Whoa, what? Whoa, 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 whoa. Just a second here, guys. What the? Wait a minute. Sorry, something's bothering me. How did I get a 5x up there? 3 plus 2 is 5, fine. How am I also thinking? I think I just got a 5x. How did I get a 5x down there? What? Oh, dummy. Dummy, dummy, dummy. Plus 3. I meant to put a minus 3 here, guys. I'm sorry. So can you guys, let me start again here. I was thinking of it as minus 3. Without putting a minus there, I don't think the problem is nice.
I have a question.
Yes.
So, like in the other problems, you know how it's supposed to be like equal to the middle term or whatever? Why isn't it equal?
So why isn't it equal to the middle term?
Yeah, I thought that's what it's supposed to be. Like equal to the middle.
Which is supposed to be?
Like the and then problems over there. Yeah, like the 1 and the 2 equal to 3 when you add them.
Oh, okay, yes. That's a good, I gotcha. So yes, over here, because the leading coefficient was 1, like we have an x squared, in that kind of factoring, you're right. That's a good judge. The sum of these will be equal to the middle term. That's right, 3. So like minus 1, minus 2, add them together, you get minus 3.
Isn't there like another way you can do this, like the little bridge thing?
I remember on the example, I've always learned slip slide method. That's the way I've always learned it, but everybody calls it something different.
Slip.
Where you multiply the 2x and the 3 and you get 6, and then you do whatever adds up to be.
So I mean that's a
Yeah.
that's a strategy.
I got the same answer, I just learned it a different way.
You done this one? What'd you get?
No, not that, I'm talking about 6. I did 6 a different way, but got the same answer
How did you do it?
using the method I learned in high school.
Can you explain that method? I mean, just tell me what's right. I'll write it. I will be your puppet.
All right.
I'm your puppet.
Then
I'll start out here. 2x squared plus 7x plus 3. Then what do you do?
Okay, so I've always learned to multiply the first number by the last number. So 2 times 3 is 6.
Uh-huh.
Okay, so then you would get x squared plus 7x plus 6. And then you add to find out whatever the middle number is.
There's no equals here, actually, right?
Yeah, there's not an actual equal sign, but that's just like what it is.
Let me get rid of that. That's not equality. You didn't say that either, so I'm not putting that on you. So you said x squared plus 7x plus 6.
Then you figure out like whatever would add up to give you your other, like the middle term, like you did on the example 1, 2, 3.
Whatever would add up to give me my middle term.
So that would be like, I don't know. I can do it better than I can explain it.
Ah,
So
well, I mean,
I can come over and like write it. Like,
I don't mind you if you want to.
yeah, I can do rough.
I will, let me, there you go.
Okay, so ux plus 7x plus 3, and you got the same thing would be squared. X squared plus 7x plus 6. What adds up to give you that would be. I'm sorry, I can't.
You're fine.
So then it'd be. Is that right? We're trying to find this one. Is that right? How did that? I got myself lost. We always did it to add up to this one. I can't figure it out. Hold on, I'll have to do it and look at that at my paper. But we always did it on this one. But you're saying to do it towards this one. Could be 2 and 3. Hard for me. we did it a very different way, but we did it like this, and then you figure out whatever this number would be.
Uh-huh.
You figure out whatever this number to be, and then you divide it by 2. And that would give you this answer. You just multiply whatever this, like this big number is,
Uh-huh.
and you get the whole thing. That's the way I've always learned it. That probably makes no
So
sense.
you
We learned like we drew like a bridge over the equation.
uh-huh.
You know what I'm talking about? But I can't remember how to do it, and that's the way I did it.
Oh,
Yeah,
yeah.
it's
Well, yeah, this I know about.
Yeah, and then you just
Yeah, that's how we did it. You multiplied this one,
Yeah.
like that one, and then you divided it by whatever this big number was. That's what we always did it.
yeah.
Whatever
Huh.
this
I
number
can't
was.
really remember how I did it.
Yeah, I
But
can't
that's how
remember
we
it,
learned it.
but yeah, this is how we learned it.
So you sure what you're remembering is for the 2x squared kind of problems?
Yeah, it's
Or
only when there's like a number in front of the x.
Yeah, it's only for if there's a number in front of the x.
so
Because
you,
it gets you back to this, so you're back
so
to
you,
this.
you take the problem which is given, you change it to something else, and then you divide your answers by 2 to get the answer or something? Or
You're pretty much taking it from where it has a coefficient to where it has no coefficient in the front, so you're
Uh-huh.
taking it back like this. But to make sure that you're using the same one, you would divide it by whatever the coefficient would be.
Huh.
But we
Okay.
always call it slip slide and divide.
I'll have to look it up. Like I'll have to.
Look, I'll show you. I'll send you a link.
Okay. I will look into it, and if I can figure out the method, then I'll teach it. But as you know, like you can't.
Oh,
Are you-
yeah, you can do it the way you've been doing it. I think that's the way I've always done it.
Yeah, I've learned the bridge way.
I was never really. I was personally never really taught a method. I just try to do it, and see, and just mostly I always hope that there wasn't a 2 in front, so it's easier. I mean, all of these methods that we're talking about, they can fail, and so I can. Let me show you how I know that. We'll finish this example. So I guess you're right. So the thing is, I'm anchoring my logic on the fact that the constant term has to come from multiplying the constant terms. That's the thing. That's the thing I anchor my logic to, is that this -3 has to come from a multiple of whatever I put here and here, right? So that means that I'm either going to put a 1 and a -3, or a -1 and a 3. Those are kind of my two choices, right? And so as you think about putting this and that, or that and this up here, the question is, how can you get back when you multiply to get just a -1, right? So since I want a -1, I want that 2 to win, which means I put the -1 over here because I know that that's going to multiply by that and give me a -2. And oh, wait a minute, I got a 3. I'm an idiot. Duh. Sorry. How? Look at this. Now this is really dumb. Look at this. I put this. Curses. I guess there are. Oh, you know what? There are more choices, aren't there? I'm just not. I'm not thinking clearly yet. We could also do this, right? Or you could do this. I think that those are the. Actually, there's 4 choices, aren't there? Because I could put -1 here, and I could put 3 there. I could put 3 here. I could put -1 there. I could put -3 here, or I could put 1 there, or I could put 1 here, and I could put -3 here. And those, like, there was in these problems, there was no, like, in these problems back here, I could either put a -1 here, or I could put -2 here, or I could put -2 here. I could put -1 here. Those are not different choices because it's just x and x on both sides. Here there's this 2x, and it spoils that, like, symmetry. So there are actually 4 different sort of flavor choices once you write the 2x there and you think about that going to those 2 things. And so, yeah. So which of these 4 choices should I choose to get back -x here? What do you guys think? Choice 1, 2, 3, 4? I think we want this one. See, because if I put minus 3 here, and I put plus 1 over here, I think we're in business, because, see, I get minus 3 plus 2, which gives me back the minus 1. But you, in your heart, you know that the slip, slide, and divide method is easier. Is that what I'm being told?
I mean,
Is that what's behind the mask?
yeah.
Okay.
Okay, I figured out what I did wrong, but we can talk about that first.
Oh, okay. Let's go back to multiplication, right? What if we took the square root of 2 times x plus 1 times the square root of 2 times x, plus 3? Well, I guess if I do that, it's not going to be especially interesting. But what if I did, oh, come on, minus 1 instead of 3? 3 is going to make it 2. 3 would not serve me in the sermon I'm trying to preach at the moment. So what happens when you multiply this out? You get what? Square root of 2x squared, right? Plus square root of 2 times x minus the square root of 2 times x, yeah? Minus 1. What's the square root of 2 squared? It's 2, right? So this would give me 2x squared minus 1. So my point to you is if we're given 2x squared minus 1, and then we try to do this, it would not be wise, right? That's not going to work, because that's not actually how it factors, right? In fact, this is part of a more special pattern. I think I told you guys already, right? Difference of squares, right? So this is a difference of squares problem. So you can look at this as, square root of 2x squared minus 1 squared. So think of that as a squared minus b squared, right? So that's a minus b times a plus b, so to speak, which in this case is square root of 2x minus 1 square root of 2x plus 1. So, what I'm trying to say is this: break the 2x squared plus stuff into 2x times x plus something. It's a possible way to factor, but it's not written in stone. It has to factor that way, right? Let us look at some more examples. To be honest with you guys, I'm really starting to be driven to the opinion that I should teach you the right way to look at a quadratic now rather than later. Hmm? No. I will continue with my examples then. So x squared plus 14x plus 48. Now, thankfully, I got rid of that pesky 2, right? So anyway, I'm trying to say about the 2 is I will think about it more and see if I can come back to you guys with like a more rigorous, overarching strategy for how to deal with those problems, as opposed to my just write down 2x and x and plug numbers in and see what happens method. But I'm telling you, that plug numbers in and see what happens method will take you a long way. Because the thing you're telling me about is more complicated, right? And if you forget a little bit of it, then you're kind of up a creek, right? Like if you half remember that slip slide divide thing, it's hard to repair it and like solve the problem, right? But what I'm doing there involves very little technology. I mean, you're building a deck with like a impact driver. I'm building it with a hammer. I mean, the hammer's going to take longer, right? But it's easier to use. It's harder to build the deck, though. I don't know. Each tool has its purpose. What do you guys think here? 48 is what? Man, 48's all kinds of things, isn't it? It's 48 times 1, right? It's 24 times 2. It's 12 times 4. It's goodness gracious. What is it? It's so many different things. It's 8 times 6. What's that? 12 and 4, but 12 plus 4. So, Olivia, is it? Olivia, you were telling me add the numbers to get the middle term, right? I mean, that's good advice. 12 plus 4, that gives me 16, right? So the one I want is 8, 6, right? The reason that didn't work over there is because of the 2. Yeah. So given that comment, we already know what we're going to do. If we have 16x plus 48, what do we do? What if we have x squared plus 26x plus 48? Or x squared minus 26x plus 48? So my example 10 is kind of long, but this is a family of related examples, yeah? They all kind of involve the same underlying arithmetic. What we got? Oh, I'll do the easy part. X, 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 X. Aha. So how do we get the first one? You guys tell me. Plus what? X plus what? 12 and 4, right? Now, why does a 12 come first? Is correct. The answer is it didn't have to. You could have put x plus 4 times x plus 12. Same answer. Polynomial multiplication commutes. All right? How about the next one? 24 plus 2. No, it was 2. It was 2 and 24. Sorry, I'll stop being an idiot. How about the next one? Let's be honest, I'm not going to stop being an idiot. It's my brand. What's that? 2? I was just being silly. This is x plus 2 times x plus 20. I mean, that's the same answer. Yeah, how about this last one? It's not the same. There's a big difference. There's a minus here. See, this I could also point out minus 48 times minus 1, or minus 24 times minus 2, or minus 12 times minus 4, or minus 8 times minus 6. These are all other ways we can get 48. Say minus what? Minus 24 and minus 2. Great. What happens when the constant coefficient is negative? Then the game changes a little bit, right? Like, what if I've got x squared minus 2x minus 48? How's that work? I'll do the easy part. How do you get minus 48? A negative and a positive, right? So we could do minus 1 times 48. We could do 1 times minus 48, right? Et cetera, right? We could do, 6 times minus 8. We could do minus 6 times 8, right? So my internal logic for these ones is like, okay, if I've got a negative, that means I have to have a plus and a minus, right? And if the middle term is negative, that means that whichever of my factors is bigger, I better make negative so it wins in the multiplication. So like that minus 2 says I should go with the minus 8 and 6 option, because minus 8 plus 6 is minus 2, right? Again, we add the numbers and get the middle term, right? So we're going to go with plus 6 and minus 8. I'm going to take a short break from examples and just share a little bit of theory here with you, because it's in our interest. So what we're doing, if you look at it like generically speaking, is we're trying to take oh yeah, it's you can just walk in the back. If you walk past the partition there, my office is the second door before you go through the other door. It's all good. Okay, so I'll keep it simple. I'll suppose we're looking at something like x squared plus, let's say, bx plus c, right? If we're looking at that problem, we're trying to factor it into what? X and, x plus, I don't know, we need to come up with some names for these numbers. What do you guys want to call the number? I need letters I haven't used already. I'm going to use alpha. No, that's not going to give you guys joy if I use alpha. What's that? Use what? B? D? Oh, D, as in like dog. And x plus e. I like it. So my question is, what is this D and E that we're looking for? Well, multiply this out, what do we get? X squared plus EX, right? Plus DX plus DE. In other words, x squared plus E plus D x plus DE. And so this is why we have these two pieces of advice. One of which I gave you, and the other which Olivia was, championing, is that, two things we need to look for, right? One is that C is equal to D times E. I keep harping on that. We're looking at the constant term, and the thing we're trying to factor has to be the product of the numbers in the factorization, right? And then the other is that the B has to be equal to the sum of them. Right? And that's actually those are good guidance for figuring out the factorization, right? So we have x squared, plus 112 x plus 111, well, plus 112. Where did I get 112 from? What's wrong with me? But let's say 111. So I need to think of like what's my E and what's my D here, so to speak, 111 and 1, right. There are endless examples like this. Like here's another one, x squared plus 49x plus 48. Anytime your middle coefficient is like one more than the constant term, it always factors kind of like this. X plus 1 times x times what? See the pattern? Okay. Now, let's see here. So I hope this is enough of a review of factoring that you have a good chance to do some on your own. Let's take 5 minutes to redo some on your own here. Let's see here. Let's try to work out example 9, exercise 9. You guys try exercise number 9, which is you're supposed to factor the expression y to the 8th, yowzers, minus 4y to the 7th plus y minus 4 equals 2. Just to factor that. That's example 9. Actually, the instructions for exercise 10 are relevant to example 9. Exercise 10 says factor by grouping. Actually, factoring by grouping is the way you want to do exercise 9 as well. Exercise 11. Here we're supposed to, we have t to the 4th minus 11t, oh, t squared rather. Oopsie, t squared minus 11t plus 24. Factor that completely over the reals. Example 12, we've got, ooh, look, 3y squared, ooh, 3, minus 12y plus 12. We're supposed to factor that. So you guys be working on those. Exercise 13. Here we've got 11a plus a squared plus 18. We're supposed to factor that. Exercise 14. This one we've got a 14 s to the 4th minus 33 s squared plus 18 s squared. Oh, well, that's not too bad. It looked worse than it was to start with. So chew on those here. So I'm gonna give you guys a big hint. This first one we should think about as y to the 7th times y minus 4 plus y minus 4. That's what you got to see in order to do the factoring there. All right. So you guys want to help me with exercise 9? What do we do? Can you tell me what the answer? If I have this, I see I can factor out y minus 4, right? If I do that, I've got y minus 4 times what? Mm-hmm. Yeah, y to the 7th plus 1, right? And that's as far as we're going to go with that. It is true that y to the 7th plus 1 can be factored into a product of things, but we do not want to do that in here. How about this next one? We're supposed to factor by grouping, which means to strategically use the distributive property. Look for commonalities in terms. So like this one pops out at me. That's x squared times x plus 3, right? And once you find 1x plus 3, you hope you can find others, right? So how about minus 6 times what? X plus 3. So we got this x plus 3. We can factor that out. And we're left with x squared minus 6. Can we do better? We can do better. That is the difference of squares. So we can break down that quadratic term further, right? 6 is equal to the square root of 6 squared. Think of it that way. So this has the pattern, it's a difference of squares. And so we can write this as x plus 3 times x minus the square root of 6 times x plus the square root of 6. There you go. Now that last step I made, whether or not you need to do that step depends on the instructions. If the instructions just say factor the polynomial by grouping, we could stop short of the last step. However, if the instructions say factor the polynomial completely over the reals, then we better go to that last step. So what does it mean to factor completely? It means to keep factoring as long as you can. My example 9, the answer is not factored completely. Nor would it be an appropriate question for this class to factor that completely. All right, you guys help me with the next one. I'll start us out. T times something, t plus something, maybe like that. And we need 24 is, what is 24? How does it relate to 11? Like 24 is 6 times 4. 6 plus 4 is 10. That doesn't help us, is it? Oh, but 8 and 3, right? 8 and 3 are good. 8 times 3 is 24. But we got this minus, right? So we need what? T minus 3, T minus 8. Yeah. So I hope you got that. Everybody get T minus 3 times T minus 8? Exercise 12. What should we factor out? I think we should get that 3 out of the way, shouldn't we? Because if we can get the 3 out of the way, then everything gets so much easier. So that's 3 times y squared minus 4y plus 4. So we're going to have 3 times y like that. How do we get a 4? 1 times 4, 2 times 2, right? Minus 2 times minus 2, minus 1 times minus 4. What do we want? Yeah, I think minus 2 is the way to go here. And the reason for that, of course, is when we multiply minus 2 times minus 2, we get back to 4, right? But then we also get a net of minus 4 from multiplying, this with that and that with that. So the bridge thing you guys are talking about is just like that organizing diagram for how to multiply polynomials, right? Like if you have a plus b times c plus d, the way you multiply is like that, and then like this, right? And like this, and like that, right? You need all those, something like that. You draw a picture like that to organize your thinking. Some people say FOIL, first, outer, inner, last, or something like that, right? Okay, how about the next one? So first of all, this next one here, I know, I mean, come on, write it in the right order, right? A squared plus 11a plus 18, right? So that's a, and how do we get 18? Overshot a little bit. See, 18 is 3 times 6. It's 1 times 18. It's, what else is it? 9 and 2. And 9 plus 2 is 11, so probably should go with that. So a plus 9 and a plus 2, that should work for us here, right? Because it gives us a 9 plus a 2, which is 11, and 9 times 2 is 18. Right? How about this next one? Well, I think the first thing I'm going to do is to collect like terms, right?